having an interdisciplinary science centre means that you have no boundaries between different disciplines, and so you can really think across disciplines, which is, I think, important.
We're here at Oxford in the United Kingdom. Behind these walls, so different from the architecture of the city and its famous universities, is located the Kavli Institute for Nanoscience Discovery, a scientific research centre recently set up by Dame Carol Robinson. Following an unusual career path, Carol Robinson has always worked in mass spectrometry, a technique for studying chemical structures in the gas phase, observing their trajectories and measuring their mass.
All of biochemistry really is about how do you understand things that you can't see. Proteins are too small for us to see. The cell is too small for us to see. How do we understand how these things work? And mass spectrometry is one of the ways that we understand things that are too small for us to see. With mass spectrometry, you can measure the weight and the charge of anything.
And that's a really key piece of information if you think about it, because everything on the Earth is made up of atoms, and it's the different arrangements and organizations of all of those individual atoms that makes up a molecule. And so by weighing each molecule or each ion, you actually learn about what that chemical identity is or the molecular identity. Generating collections of these molecular weights tell you something about what's changed biologically in the system.
Formerly confined to the study of denatured chemical or biological structures, it is thanks to Carol Robinson that mass spectrometry now finds a wider range of applications. Having started out as a lab technician, Carol Robinson then earned a PhD in chemistry, paused her professional career to have a family, and then returned to science at the turn of the century. Her goal was to observe and study proteins in their non-denatured form via mass spectrometry. The scientific community initially viewed the idea with considerable scepticism.
My work, it's important for mass spectrometry to keep proteins in their folded state. So I don't want to unfold them and sort of cook them almost so that they're denatured. I want them to be as they are, as close as I can get them to their cellular state, to how they exist in our body. The challenge is, of course, to keep the states like that and to keep them as cool and as folded as possible. And you have to adapt to mass spectrometers, and that was something that I did with great passion early in my career, suggesting or even implementing modifications that would make this possible.
In 2008, Carol Robinson showed it was possible to observe undenatured protein complexes by first isolating them in soap bubbles and then injecting them into a mass spectrometer. She successfully established this technical innovation, notably making it possible to observe membrane proteins and, above all, their interactions with the surrounding environment.
In order to analyze those proteins by mass spectrometry, we need to load them into this little needle here so that we can introduce the proteins into the gas phase, into the mass spectrometer by this technique called electrospray. These little needles here, we prepare these all in-house. We draw them to a really fine point, we coat them in gold. And this is one of these key inventive steps that actually enables the technique.
By using mass spectrometry in this way, we're able to look at membrane proteins particularly in different ways to the ways that they're studied in other labs. So, for example, very recently we observed signaling across the membrane, and really you could only do that in a mass spectrometer because it's a very heterogeneous reaction. So you have to be able to separate everything by mass to observe everything individually.
These innovative techniques make it possible to better study certain diseases, how they evolve, and the efficacy of certain targeted therapeutic treatments.
So if I know the exact weight of my protein and I get something that's a bit heavier, then I know it's binding something else. Or if I can add something to my protein and then see that it binds something else, then I can follow reactions in the cell. I can see which proteins are good at binding, which proteins are bad at binding. And if I know which things in the environment affect my protein, then I can understand how drugs might affect it, how we might modulate it with drugs, how we might treat protein disorders with drugs.
We have a lot of biologic drugs these days. You know, things are getting bigger and bigger and bigger, and they're getting more and more complicated and very difficult to characterize. But if you're going to give them to people, you want to make sure you're making the same thing every time, right? It's still a drug. And I think, the technology that we work on can play a big part in doing exactly that.
The scientists working with Carol Robinson continue to develop the use of mass spectrometry for observing increasingly complex undenatured protein structures. Thus, scientific knowledge and leading-edge technology go forward together.
When you're writing proposals with Carol or designing experiments, she tends to ask very, very grand, big questions, a lot of what-ifs. Even the data that you're seeing here on the screen has been possible because of these big questions that Carol asks and because she really pushes and makes you think about what is it that you need to take the next step and to change the field and to be able to collect data like this and get information like this.
It's very collaborative, and Carol's keen to let people explore the field themselves and to have ideas and test them and try things, and she's never afraid to just have a go and see where it might lead you scientifically.
This and this. So it's good to have people there all the time who continuously, say, oh, can you try this? Could you do that? Can you measure that? Can you give us more information? And then you're always interacting with the people who are ultimately supposed to use the technology for, and that makes the process a lot more efficient.
I always like scientists to come with ideas. If they're all my ideas, then that's not great. But if I've got 20 people and they're bringing ideas to the table, that's much better, and that goes well, I think.